So welcome everyone to our seminar today. Our speaker today is Matthew Lorentz from Hawaii. So Matthew is going to tell us about Hochschild cohomology of uniform row algebras. Please.
Thank you, and thanks for inviting me and for everybody to coming today. So to start off with, I'll just give a little outline of what we're going to see. First, I'm going to give some definitions that are probably familiar to everybody, but just to familiarize you with my notation, and in case you don't know. And then we're going to talk about the main goal of what I'm going to try to do today. And a lot of stuff that I'm going to be using comes from Sinclair and Smith's book, The Hochschild cohomology of von Neumann algebras. And then I'll talk about the trick that they use in order to make everything work. And then I'm going to talk about L-infinity multimodular maps for a minute, and I will define what those are. And then I'm going to talk about the obstacle to the method that Sinclair and Smith use and how I get around that, and then give a brief sketch of the proof of the main result that I'm going to give today. So uniform row algebras, there are a lot of ways to describe these, but this is the way I'm looking at them for this talk. So if we have a metric space and an operator in the bounded operators on square summable sequences, we're going to say that it has propagation of at most R if it's matrix entry, that is taking the inner product against the canonical basis elements of L2 of X, if that's 0 whenever the distance between X and Y is greater than R. And we'd say that that operator has propagation at most R. And then I'm going to denote the set of all operators that have propagation at most R by that. And then we say the algebraic uniform row algebra is the set of all operators that have propagation that's finite. And then we take its norm closure in the inherited norm from the bounded operators, and that is the uniform row algebra. Some examples of uniform row algebra. I really like to think of these things as matrix. So if we're taking the uniform row algebra over Z, we would have a copy of Z going that way, copy of Z going this way. It's a great big matrix. And the finite propagation ones, the non-zero entries lie in a band by the diagonal. And then we take all of those and take its norm completion. Another way to look at it is if we have gamma a group, we can take the uniform row algebra of that group, and that would be the cross product of L-infinity of gamma with gamma. Okay. And for this talk, we're going to be exclusively interested in uniform row algebras that are associated to bounded geometry metric spaces. And by that, bounded geometry metric space, I mean, if we take a ball of radius r, anywhere there is an nr such that the ball contains at most n sub r elements. So we can take a ball, we can place it anywhere, and that ball will contain at most nr elements. A few examples are the integers. If we have a radius r that's a natural number, then a ball anywhere is going to have 2r plus 1 elements. Another way we could look at it is if we have a finitely generated group, giving the group the word metric, it's not hard to see that that will have bounded geometry also. So the main result for today is that the Hochschild cohomology of uniform row algebras associated to bounded geometry metric spaces vanish in all dimensions. So this whole project started, I was looking for a bounded outer derivation on the uniform row algebra, and Rufus and I ended up showing that there are none. But that can be restated as the first Hochschild cohomology vanishing. So then from there, it's natural to ask what happens in the higher dimensions. So as I said before, most of the techniques I'm going to use today come from Sinclair and Smith's book, The Hochschild cohomology of von Neumann algebras. And so for notational simplicity, because we're going to have a lot of parentheses and stuff. I'm just going to let A be the uniform row algebra. I'll let script B be the bounded operators on the square summable sequences, and we'll let little l be the bounded sequences over X. And in their book, Sinclair and Smith show that the continuous Hochschild cohomology of maps from the uniform row algebra to the bounded operators that are L infinity multimodular, and I'll talk about multimodular in a moment, are isomorphic to the Hochschild cohomology of multilinear maps from the uniform row algebra to the bounded operators, which in turn is isomorphic to the continuous Hochschild cohomology of the bounded operators to themselves. And then they show that that is zero. And they show this in more generality. What they show is that if we have a von Neumann algebra that's hyperfinite, then its Hochschild cohomology to itself is zero. Now, our goal is going to be to show that these L infinity multimodular maps that go from the uniform row algebra to the bounded operators are in fact isomorphic to the continuous Hochschild cohomology from the uniform row algebra to itself. So I'm sure a lot of people are familiar with this, but to get used to my notation, the Hochschild complex, first we start with a Cstar algebra, and we let this fancy V be a Banach A bimodule. And then by this script L sub C to the N A to V, these are the N multilinear maps from A to the module V that are separately continuous in each coordinate. And that's when n's bigger than 1. And for n equals 0, we just let it be this bimodule. So these are the maps that we're considering. And if A is a bimodule over itself, as is custom, we'll just write it by itself. So the co-boundary operator, it moves up a dimension, and what that does is we take in n plus 1 coordinates, and then we turn it into a sum where the first coordinate comes out, and then we have this alternating sum where we're putting the j and j plus 1 coordinate together. And then finally, for the last one, we let the last coordinate come to the outside. And when n equals 0, well, this is the derivations case that I was mentioning before, where it's an inner derivation given by the commutator bracket. And of course, a straightforward calculation, not an easy one, but a straightforward one, shows that we apply the boundary map twice, we're going to get 0. And then, as we usually do with cohomologies, we build the Hochschild group by taking the kernel of the boundary map and modding out by the image of the previous boundary map. And we call an element in the kernel a cocycle, and an element from the previous boundary map a coboundary. So multimodular, as promised. So if we have a sub C-star algebra, say B, of the algebra that we care about, A, I'm going to use the notation where I'm using this colon to indicate multimodularity. And that means if we have a B in our subalgebra B, if it's against the first coordinate entry, then we can bring it out front, like so. And if we've got one, say, in a coordinate behind the j minus 1, then we can move it across the comma into the next coordinate. And then if it's on the end, it can come out side like so. And that would be a B multimodular map. And we can form its Hochschild cohomology in the same way that we did the others. Okay. So the trick that Sinclair and Smith are using is they start off with the inclusion map from the L infinity multimodular maps just to the regular maps. And then that'll induce a homomorphism between the Hochschild cohomologies. And to show that that map is in fact surjective, they build this map Kn, which is quite a complicated map that we'll see in a moment. That's going from the n-dimensional maps to the n-1 dimensional maps. And so if we take a cocycle, say phi, we modify it by this co-boundary, where we're taking the boundary of Kn of phi. This is going to be L-infinity multimodular. Okay, so to build that map, we first need an averaging operator. We're going to average over amenable groups. And in this case, the amenable group that I'm going to use is the unitary group of L-infinity of x. We can imagine L-infinity of x sitting inside the uniform row algebra over x as a diagonal operator. And so that has propagation 0, of course, it's in there. And then since L-infinity is abelian, of course, its unitary group is abelian. So it's amenable. So there exists an invariant mean on L-infinity of u. So we're going to fix one of those means. And then if we take an element B in the trace class operators, and we take A in the bounded operators from the unitary group to the bounded operators on the square summable sequences, this map psi sub BA would take in U and bring it to the canonical trace of B times A of U. And that's going to be a bounded map. So that's in L-infinity of U. So from that, we can build a bounded linear functional, taking an element B in the trace class operators and sending it to phi of psi sub BA. And since the trace class operators are the pre-dual of the bounded operators, we obtain an element in the bounded operators on the square summable sequences. I'm going to use this notation for that element. But the integral notation is just meant to be suggestive. If U was compact, well, then this mu would actually be a Haar measure. But in this case, it's not. So this is just a mean. But it turns out that map enjoys many of the properties of an integral, and that's why we use the notation. If we take a bounded operator from the unitary group to the bounded operators on the square summable sequences and just map it into that averaging operator, that map is going to be contractive, it's going to be linear, invariant, and it's going to act as the identity on the constant functions. Moreover, for any element in the bounded operators on the square summable sequences, we can bring it in like so, or we can take it out like so. So this is behaving very much like an integral, except for that we lose countable additivity. It is linear, but it is only finitely additive. So from that, we can start constructing this map Kn. Now the map Kn, first we start with a map we call J1, and applying it to psi, we take in a vector, and what we do is we stick it in the averaging operator, where we're averaging over U star in the front and then U in the first coordinate. Then we also have this map GK that takes in a vector, and this time we put the U star behind the kth coordinate, U and the k plus 1, and then line up the rest of our vector afterwards. And then JK plus 1, what we do with that is we take the previous map JK, and then we add it to -1 to the k, and then we apply the GK map to the identity minus the boundary of the previous JK map. And then Kn will be our Jn when we get high enough up there. So our goal is to show that these L-infinity multimodular maps from the uniform row algebra to the bounded operators is isomorphic to the operators that take the uniform row algebra to itself. So as a first step, I'm going to show that these maps that are L-infinity multimodular, that they're L-infinity multimodular means that they have to land back in the uniform row algebra. They can't break outside of it. And so we will have not necessarily surjective homomorphism between what we're trying to show as isomorphic. Okay, but first we need a definition. So epsilon r approximated. So if we're given epsilon greater than 0 and r greater than 0, an operator, say t, in the bounded operators on the square summable sequences, can be epsilon r approximated if we have another operator s that is of finite propagation, such that, well, of propagation less than r, such that t and s are epsilon away from each other. And note that if an operator can be epsilon r approximated for all epsilon greater than 0, then it's in the uniform row algebra. So first we'll take a phi in the L-infinity multimodular maps and a vector in an, and we're going to let epsilon be between 0 and 1. And we're going to set m to be the max of the norm of all of these xi's, and then we're just going to add 1 to it. And then by the previous definition, since these are all in the uniform row algebra, we can break them apart. So each xi equals ai plus bi, where ai is a finite propagation, and bi, we can make that as small as we want. So we're going to take the minimum over that. And then because of this plus 1, we also have that each of these ai's is less than m. So if we have one of these b's coming from here in any coordinate of our map phi, then it's going to be bounded by epsilon over n. So then, using that phi is multilinear, we can break phi into a sum where our first term, it has nothing but finite propagation arguments in the coordinates. And then the rest of these, they all have b's in one of the coordinates. So the rest of those will add up to having a norm less than epsilon. So really what we need to do is show that if we're just giving it finite propagation argument operators, that it itself will be finite propagation at the end. And here the r that I'm using is the max of all of the ri's that I get from these. Okay. So let's let P sub x be the projection onto the span of the Dirac mass at x. And let's consider this. So what we're doing is we're putting these projections, they're rank 1 projections in L infinity of x, and we're just putting them around each of these a's that we have. And if the distance between x and y is bigger than n times r, well, by the triangle inequality, we have that, so that if any one of these were these k sub t minus 1 k sub t, those are elements of x. If the distance between one of these is less than r, then there's going to be another one whose distance is greater than r. So that when we surround it by this p sub k sub s minus 1 around and p sub k sub s around the as, well, that's the matrix entry of as, and so that has to be 0. So for all of these kj and x, if the distance between x and y is greater than n times r, well, this whole thing is going to be 0. So since these are convergent, since this series converges strongly to the aj, then if we put another finite rank operator on the other side, this projection, this rank 1 projection, say, well, then this is going to converge in norm. And since these are separately continuous, what we'll do is we'll just sum up over one of them and then bring it into the next coordinate using multimodularity, and then sum over the next one, bring it in using multimodularity. So if we take all of these sums one at a time, it equals 0, but it converges to px phi of our argument py, which is its matrix entry. And whenever this distance is greater than 0, one of these is going to have to be 0. So this is of finite propagation, as we were trying to show. So basically, we can write that as the sum of something less than epsilon and something of finite propagation. So it's in the uniform row algebra. Okay, so now we've got this not necessarily surjective homomorphism that we were trying to get, and we would like to apply the trick that Sinclair and Smith use. So we take a cocycle, we modify it by the coboundary, and then it'll be L infinity multimodular. However, Kn of phi might be landing in the bounded operators once we take it. And then that would mean that this is not a coboundary in here. It would be a coboundary in the maps from A to B, but it might not be a coboundary in there. So to remedy this, we first use that the continuous Hochschild cohomology is isomorphic to the normal Hochschild cohomology, which I don't have time to show that today, and it's technical and there's not a lot of content to it. So, but it's in Sinclair's and Smith's book in 3.3 and 3.4. But then assuming that, we use recent results from Braga and Farah from their paper on the rigidity of uniform row algebras to show that if we've got one of these cocycles phi in the weakly continuous maps, then applying Kn of phi to it, we're going to land in the continuous maps. And note that I'm just looking at this as a vector space. Of course, that's not complete. Okay, and to state this result, we're going to let Blackboard B be the closed unit disk. And for a set I, we're going to let Di denote the usual product spaces of functions. And we're going to write our Di's as tuples, lambda equals all of these lambda sub i's indexed by the product set. Okay, so what their lemma says, and I think it's a very powerful lemma, is that if we have a metric space with bounded geometry, they show it much more generally, but for our purposes, we'll let I be countable. And then we have a family of operators indexed by I that is uniformly bounded and in the uniform row algebra, such that for every lambda in Di, the series where we're going to add them up lambda I sub I times A sub I, if it converges weakly to an operator we're going to call A sub lambda that is in the uniform row algebra, then for every epsilon greater than x0, there exists an R greater than 0 such that A sub lambda can be epsilon R approximated for all lambda in that product set. So there is a single R for every lambda. Okay. So let's get to an example / sketch of the proof. This notation gets really crazy really quick because we take several boundary maps in these operators. So I'm just going to show it for the two-dimensional case. So say we've got a phi in the bilinear, separately weakly continuous maps. Then we're going to show that K2 of phi is in the separately continuous maps. So by the definition of Kn, we can write K2 is J1 minus G1 plus G1 boundary J1. And since all of the terms in this sum are handled the same way, we're going to take on the most difficult one, the G sub 1 boundary J sub 1. Okay, so applying these maps, since we're applying everything to the argument, we go in reverse order. So first we apply G1, we take it to the averaging operator and put a V in that coordinate, we get a V star there. Then we apply the boundary map. So we get these three terms inside of our averaging operator. Then we apply the J1 map. So we end up averaging again in each term. But then since our averaging operator is linear, we just pull it in and we'll have three terms under the averaging operator. And note that this, no matter how high of a dimension we go and we are expanding it, we're going to end up with a finite sum because the boundary maps only put out finitely many terms. So no matter, as long as we're only applying a finite number of boundary maps, we're going to have a finite number of terms. So we can do this as we go into bigger dimensions. So again, since all of the terms in this sum are handled similarly, we're just going to look at this operator here and show that this one ends up in the uniform row algebra. Okay. So again, we're going to let Px be the projection onto the Dirac, the span of the Dirac mass at x. And then for an element in the unit ball of L infinity of x, we can write at that element as a weakly convergent sum, where we're just taking something of magnitude less than 1 times the projection and then summing them all up. And for any lambda in the product set dx, if we do that, it's going to converge weakly to an element in the unit ball of L infinity of x. And so specifically, we could write any unitary in L infinity of x as such a sum. So without loss of generality, we're going to assume that phi is weakly continuous from the black box from before. And if we have u and v in the unit ball of L infinity of x, or specifically in the unitary group, we can write u star phi of u a v star v as a weakly convergent sum, just summing up these, and we would be adding these one at a time again because of the separate continuity. But we can add these all up to get to here. It's going to converge to this, but then also we're going to be bounded by the norm of phi times the a that we were given for the argument. So this is going to satisfy the condition of Braga and Farah's lemma. So from here, if we're given an epsilon greater than 0, we can write this as a of uv plus b of uv, using the epsilon r approximation from before, where a of uv is going to have some finite propagation, and b of uv is going to be less than that epsilon. So if we take E sub yx as the standard matrix unit, and then we apply the trace to that matrix unit times a of uv, this is going to return the matrix entry xy of a of uv. And that'll be 0 whenever the distance between x and y is bigger than r, for all of the uv in the unitary group of L infinity of x. And since the linear functional that's under the hood of the averaging operator sends each matrix entry EYX, that's where the distance between X and Y is greater than R, since it's going to send this to 0 whenever the distance between X and Y is greater than R, we're going to have that this operator is going to have finite propagation. And moreover, since our mean is contractive, the B part of breaking up each entry is going to have norm less than epsilon. So this and this, we add them together where epsilon are approximated. So it lands back where we're supposed to land. And so this operator is landing in the correct space now. So we can, and boy, I'm talking fast this morning, I'm sorry. So if we're given a cocycle phi, we can modify it by this co-boundary, and there should be a W here, but as I said before, since they're isomorphic to each other, we're okay. But we can modify it by this co-boundary, and since we've established that this is going to land in the correct space, this will actually be a co-boundary in there. So this gives us that we can take something in here, we can modify it by this co-boundary, so it's living in here. And that gives us surjectivity. So this map is now surjective. And since from Sinclair and Smith's results, this is 0, we're surjecting 0 onto something, it better be 0. Right. So we get that the continuous Hochschild cohomology of the uniform row algebra is in fact 0. And as I said, I was talking really fast this morning, a lot faster than I was talking when I practiced this. So that's what I have for you today. Are there any questions?
Okay, before we have questions, let's thank Matthew again for a beautiful talk. So do we have any questions? So maybe I'll ask a question, Matthew. So here you consider the Cstar completion of the finite propagation operators. So if we restrict ourselves to just the subalgebra of operators with finite propagations, the union of all of them, they still form algebra. So can you say anything about the Hochschild cohomology of this algebra?
On that one, it would be difficult because when we're using this averaging operator, we're kind of relying on it being epsilon close. And so if we just consider the union of the finite propagation ones, if we don't take its completion, we're going to lose that epsilon, the ability to epsilon approximate it. And then this averaging operator, it'll end up converging in the uniform row algebra, not just the banded operators.
So, Matthew, does the technique extend to like a certain cross product? Because if the space is a group, your result implies the cross product with L infinity has trivial Hochschild cohomology. I'm just wondering in what like generality this would be true for cross product.
That's something that I plan to investigate more in the future. I haven't had a lot of time to think about that yet. I'm fairly certain that this is going to generalize to just the row algebra. and I want to investigate using other groupoid Cstar algebras generated by other groupoids aside from the one under the hood of the uniform row algebra. I haven't thought too much about cross products, but I intend to.
Okay, so do we have any other questions or comments to Matthew? Okay, let's thank Matthew again for a beautiful talk. Thank you.